We'll just wait for a few more minutes and see who else joins and then start the session. Hello everyone, this is Tanya, one of the teams assigned to the aircraft stability and control. It's not by Professor A.K. Bush. Today we'll go over the concepts that we are handling in week one and week two, and we have 23 questions. Before that, were you able to access the slides and the recording of the previous session? Is that available now? Am I audible? Can someone just confirm in the chat box if I'm audible? Okay, were you able to access the recording and the slides of the previous session from the course page? Then we'll move on. Yeah, so this is, I think we had dealt with this in the last session. So static stability is defined as the initial tendency to go back to equilibrium. So suppose your aircraft was in flight and it's subject to some gust, and the tendency of the aircraft to come back to its equilibrium is referred to as static stability. And in our case, it's longitudinal static stability because we're seeing the longitudinal dynamics, the pitch stability. Right? Then we had seen what aerodynamic center is. Aerodynamic center is the point which is independent point about which the CM or the pitching moment or the pitching moment coefficient is independent of angle of attack. So when we transfer the forces from the center of pressure to the aerodynamic center, it comes with a moment. So your forces and moments act at the aerodynamic center. Alright. So this was the linearized equation for coefficient of pitching moment that we saw. Cm is Cm naught plus dCm upon d alpha into alpha. Can anybody recall what is the only condition for static stability? From this equation, what term should be positive or negative or zero for the aircraft to be longitudinally statically stable? So what was the condition?
D alpha to be negative.
dCm by d alpha should be negative, correct? Yes. So dCm by d alpha should be negative. So your graph will look something like this. Another thing that we had seen is that we need Cm naught to be positive. Why do we need it to be positive? To trim your aircraft at a positive angle of attack. It's not a necessary condition. It's just something that we prefer. We prefer to trim our aircraft with positive angles of attack, and hence we need Cm naught to be positive. If Cm naught were negative, we've seen this in the last class. This is Cm naught alpha. Your graph will be something like this, and you will have to trim your aircraft at negative angles of attack, which is not desirable. So in order to trim your aircraft at positive angles of attack, the Cm naught has to be greater than zero. But for static stability, the only condition is this should be less than zero. Right? So I put these conditions there. So then we looked into the contributions of the wing and the tail towards this pitching moment coefficient. So you have your original equation that the Cm is Cm naught plus alpha into alpha. So what we're going to look into now is the individual contributions of wing and tail towards each of these terms. So it will be Cm naught of tail plus Cm naught of wing plus Cm alpha of tail plus Cm alpha of the wing into alpha. So this will be your final equation where you can see the individual contributions of Cm naught and Cm naught alpha from the wing and the tail. So let's look into the wing contribution first. This derivation is fairly simple. I will explain in the lectures. So you don't really have to remember these terms. If you remember it, it's great. But if you don't have to remember it, the derivation was very simple. So you just have to start with, you define your CG, define the varying lengths. So if I am going to draw it, let me just draw it here. So if you are, this is your fuselage reference line. This is your wing. Define this as your CG. As your tail. So reference point will be your wing leading edge. This is your AC wing. This is your AC tail. This will be X AC wing. This will be XCG. This will be X AC tail. So then you can start finding out the forces. So you have lift of the wing, drag of the wing, then lift of the tail, drag of the tail. Find out the various components of these forces about CG. So you need to find Cm or let's take moment. Moment at CG is force and displacement, do it for the various force components, and then you'll be able to form an equation for NCT. Then you make it non-dimensional by dividing it by, divide throughout by half rho v square S. V square S, yes. SCA. So Cy, where rho is the density, V is the phase-change velocity, S is the area of the wing, C bar is the mean aerodynamic chord of the wing. Divide the entire equation by these terms, and then you'll be able to non-dimensionalize the equation, and then you'll get your equation. Now, from that equation, I'm just writing down the terms that are contributions of wing and tail. So the CM naught contribution of the wing is given by this term. And this is the CM alpha contribution of the wing. Similarly, for the tail, we have CM naught of the tail. This entire thing, including the negative sign, is CM alpha of the tail. All right. So we can see the CM naught contribution of the wing. It has two terms. One is CM AC wing. What was CM AC wing? Where did it come from? Is it constant? Is it varying? What are the typical values? Anything? Where did CM AC wing come from? So this term just
That is for the cambered airfoil.
Yes, yes. So for the cambered airfoil, it is a positive or negative?
It will be negative.
Negative, correct. For symmetric airfoil, it will be 0. For cambered airfoil, it will be negative. And for reflexed airfoil, it will be positive. So your CMAC came because you were transferring your forces from your CP to your AC. So it comes with a moment. So that is your CMAC. So 0 for symmetric, negative for cambered, and positive for reflex. Now the CL naught into this distance comes from your lift components. CL naught, what is CL? CL is CL naught plus CL alpha into alpha. So when you do the derivation, you will have a CL naught into distance term, which is what is given here. Now, similarly, the remaining term, CL alpha into the distance is, it contributes towards the slope. All right. Similarly, for the tail you have. So for the tail, the CM alpha comes with a negative sign. Can anyone try to tell me why there is a negative sign? CM alpha tail has an inbuilt negative sign, right? So why is the negative sign there? CM alpha tail is minus VH eta CL alpha tail 1 minus rho epsilon by rho alpha. Yeah, so this is CM alpha tail. Why is there a negative sign there? You can maybe look back at your
Because the
derivation.
restoring moment will be in the
It will be
yeah,
pitched down.
it will give me the nose down motion.
Correct, correct. So you have a lift at the tail, and the moment about CG will be nose down. So nose down, our convention is nose down is negative. Pitch down or nose down, it is negative. So you have a negative sign in the CM alpha of the tail. So what were the, let's look at the individual terms so that we are all on the same page. So CM AC wing, we know what it is. CL naught, we know the linear coefficients for the linearized equation for lift. What were the other terms? Yeah, VH. What is VH?
Tail volume ratio.
Horizontal tail volume ratio. Its formula was ST upon S, LT upon C bar, where ST is the area of the tail, S is the area of the wing, LT is the tail moment arm, which is the distance between XAC tail and CG. So this is LT, right? The distance between the aerodynamic center of the tail and the CG of the aircraft. So that is LT, and C bar is mean aerodynamic chord of the wing. So this is the horizontal tail volume ratio. Next, you have eta. What is eta?
The ratio of the dynamic pressure corresponding to tail velocity and phase stream.
Correct. So we have V infinity prime square by V infinity square. So the free stream velocity seen at the tail is different from the free stream velocity seen at the wing. This is due to downward. What was downward? I think I have a slide on this somewhere. Yeah, so this, we had discussed this in the last class. So the flow above the wing and flow below the wing, they intersect at the tip. So if you see the direction of the blue arrows, so they flow in such a pattern, and when they intersect at the tip, there are vortices formed. And when the vortices are formed, these vortices travel downstream along the motion, reverse of the motion of the flight, and they travel downstream towards the tail. Due to this, the angle of attack and the free stream velocity witnessed at the tail is different from the free stream velocity seen at the wing. Okay, so what do we do to reduce this? This again, I think this was the question in the last class, one of the questions. What do winglets do? How do winglets help? It was something similar. So what winglet does is, winglet is a small upward bend at the tip of the tail. What the winglet does is that it reduces the magnitude of the vortex form. So the intersection of the flow happens at a point, and the magnitude of the vortices thus formed are much less. So that is what winglets do. Okay, so you can see that the vortices travel downwards, and into the winglets, the vortices, the magnitude is weaker. That's what winglets do. Okay, so let's get back to. Yeah. So eta was V infinity prime square by V infinity square, which is ratio of the dynamic pressure seen at the tail and the wing. All right. What else is left? Epsilon. So epsilon is defined as epsilon naught plus the epsilon by the alpha into alpha of the wing. So what was epsilon? Epsilon is downwash, the downwash that we just saw. Right. So because the tail is in the wake of the wing, there it's subject to a different free stream velocity, different free stream. So how do we mathematically represent this? Using this equation where epsilon naught is the constant and this is the slope, right? So the constant term comes in the CM naught contribution and the slope comes in the CM alpha contribution of the tail. All right. Then another point that we had seen, I think I said we'll discuss this question in the next session, was neutral point. So AC is the point about which CM is independent of angle of attack, but AC is for the wing or for the tail, for any aerodynamic surface. Neutral point is similar to the aerodynamic center, but it is for the entire aircraft. All right. So neutral point is the CG location at which CM alpha is 0, which is nothing but CM is independent of angle of attack. So at neutral point, your pitching moment is independent of angle of attack, similar to the definition of aerodynamic center. But aerodynamic center is for an aerodynamic surface. Neutral point is for the entire aircraft. Okay. So now, if we had done the derivations from there, if you had set CM alpha equals to 0, then you would have gotten this equation for neutral point. Because at neutral point, your CM alpha is 0. So when you do the derivations and you set the CM alpha term, that is this term with the individual contributions, CM alpha of the wing, CM alpha of the tail, if you equate it to 0 and replace your XCG with XNP, you get this neutral point equation. Okay, so, and then the other thing that we've seen is static margin. Static margin is like a quantitative analysis or quantitative measurement of the stability of an aircraft. So greater the static margin, greater is the stability of the aircraft. Static margin is defined as negative of DCM upon DCO, negative of the slope. And it is XNP minus XCG. So for a statically stable aircraft, will your static margin be positive, negative, or 0? For a stable aircraft.
Negative it should.
Will it be negative because let's see, your CM versus CL has this kind of a nature. So the slope CM versus CL is negative. And we have defined static margin as negative of the slope. So your static margin for a stable aircraft will be positive. So another way to see this is, so a mnemonic that I use to remember this is, it's CAN. So what it means is that the CG should be, for a stable aircraft, CG should be ahead of the aerodynamic center if it's just a wing configuration. If it's a plane, if it's the entire aircraft, CG should be ahead of the neutral point. Okay, so when your CG is ahead of the neutral point, your XNP minus XCG will be a positive quantity, and hence your static margin will be positive. So for a longitudinally statically stable aircraft, your static margin will be positive. These are the two ways. This slope is negative and there's a negative sign, so you know it's positive. And for stable aircraft, CG is ahead of neutral point. So XNP minus XCG is a positive quantity. Again, you know, so the static margin has to be positive. For a stable aircraft, static margin is positive. Right. So these are just the mathematical equations for the terms that we described before. So epsilon was epsilon naught plus epsilon by rho alpha into alpha v, where epsilon naught is defined by this equation 2cl naught plus pi pi e ar, and the slope is given by 2cl alpha v by pi e ar. VH we just saw horizontal tail volume ratio, and it's given by STLT by SC bar, where LT is the tail moment arm, which is the distance between the AC of the tail and the CG. And another equation that you need to remember is this relationship between a 2D airfoil and a 3D wing. Right. So all of the aerodynamic relations that we studied give us the aerodynamic parameters of the airfoil, but they are not the same as a wing. So if we use that airfoil to make a wing, the actual ratio or the actual slope would be different. And how are they related? They are related using this equation. Why does it happen? Because the airfoil, I had said in the last class, airfoil is a wing of infinite span. So there is no wingtip vortex. There is no interaction of the flow above and below the wing. There is no interaction. So it's the ideal case. But that is not what happens in real life. So the wing is of finite length, and there is an interaction of the flows, which leads to vortices being formed, and it does not give you the actual lift that the airfoil would have given. So it is slightly reduced. And how do we quantify this? Using this mathematical equation. So what we need to remember in using all of these equations is that all of these equations are valid for radians and per radians. So all the individual quantities in these equations need to be in terms of per radians or radians. For example, CL alpha of the wing should be in per radians for this equation to be valid. And you also get your angles in radians. All right. Then here again, you should have your CL alpha in per radians for this equation to be valid. All right. Okay. So this was the question that I had left last time because neutral point is not discussed. So now let's look into it. If the CG, or the center of gravity of the aircraft, moves backward towards the neutral point, then the aircraft will be less stable, more maneuverable, less maneuverable. So if I draw the fuselage reference line and say this is the neutral point, and this is your CG. Now the question says, if the CG moves towards the neutral point, what will happen? What will it be? Just look into it and try to get it. Less stable. Okay. Yes, less stable. Any other option? Because your options are pairs, right? So anything else? Are the others following? Please stop me at any point if you have any query. 1 and 3. Yes. So Shreya is right. So it's 1 and 3. That is the right answer. Why? So when the CG moves towards neutral point, the static margin is reduced, right? So it is static margin is P minus XCG. When your CG moves towards your neutral point, this value is reduced. So we have seen that when the static margin is reduced, the stability of the aircraft is reduced. what happens? The slope, the CM versus alpha slope is reduced. So when your aircraft is less stable, it is also more maneuverable, right? So it is easier to control the aircraft. It's easier to pitch up or pitch down when the aircraft is less stable. So all these go hand in hand. So less stable means more maneuverable or more controllable. More stable means less maneuverable. So if it's less stable, it will also be more maneuverable. So 1 and 3 is the right answer. So this is something like it's seen last class. So for a wing alone configuration, you only have AC. And for it to be stable, your CG has to be ahead of your AC. Alright, so this is a stable wing alone configuration. Now, when I add other controls, other aerodynamic surfaces, so now I've added a tail. What happens is that the effective aerodynamic center or the neutral point is pulled. So initially, the aerodynamic center was nothing but the AC. Now you can see that the neutral point is moved backward, right? Moved backward towards the addition of the new aerodynamic surface, right? So now if I add an aerodynamic surface ahead, it will move ahead. So the neutral point moves along with the addition of new aerodynamic surfaces. So this is for a wing and tail configuration where the neutral point, the CG is still ahead of the neutral point, so it is stable. All right. Now you can see a canard and wing configuration. So now the neutral point has moved ahead towards the new aerodynamic surface. Here again, CG is only slightly ahead of neutral point, but it is still stable. I just thought that we should have an idea of how the aerodynamic center moves. Okay. So next question is, when the angle of attack decreases, the moment of center of pressure will be towards trailing edge, independent of angle of attack, towards leading edge, or all of these. Just take a moment and try to tell me. Trailing edge. Okay. Can you explain why towards trailing edge? Trailing edge is the right answer. Can you explain why? Anybody else? Can you just try to, so now that you know it's towards trailing edge, can you try to justify that answer? We had seen how central pressure varies, right? So, excuse me. So we had come up with aerodynamic center because the center of pressure keeps changing with angle of attack. Aerodynamic center is a point that is independent of angle of attack. Now, center pressure keeps changing with angle of attack, so it was undesirable to perform the analysis there. At that time, we had discussed how it varies with change in angle of attack. Right? Maybe refer to your notes or the previous session or try to get this, try to justify the answer. was there in the last session. So if you have the slides or the notes, please refer to it and try to justify this answer. It is towards the gradient. That is the right answer. It's something to do with the pressure distribution, right? So because it's in the center of pressure, so it has to be something to do with pressure distribution. So you use that to come up with the reason for this answer. So the aircraft surface changes. Let's just go to the figure that we had seen in the last session. So the pressure distribution of over an airport is given in this figure. So with change in angle of attack. So initially, if it is at 4 degrees or at some angle of attack, you can see the pressure profile. So above the surface it is negative, below the surface it is positive. Okay. So the central pressure is somewhere here, and that is where your lift and drag act. Now, when I increase the angle of attack, the pressure profile or the pressure distribution changes such that your the effective, the center of pressure or the location of the effective pressure happens, it moves a little towards the leading edge. So now your lift and drag act at this point. Now, when I reduce the angle of attack, the pressure profile moves towards the trailing edge. Moves towards the trailing edge such that the center of pressure also moves towards the trailing edge. Lift and drag act in such a way. So change of pressure distribution over the surface of the airfoil with change in angle of attack is what changes center pressure. How it moves, and then the centroid of the pressure profile is what gives us CP. This is the graph that is used to depict how much the pressure changes. And the upper surface is negative pressure, lower surface is positive pressure. At zero angle of attack, it's all balanced out. You have similar profile distribution, pressure distribution here. When you increase the angle of attack, you can see how it changes. So this is the figure that we've seen in the previous slide, right? So it's something like this. Okay. Now we'll look at control. I think this was also discussed in the week 2, if I'm not wrong. Don't stop me if this was not discussed, and we can just go back to the other questions. So what is control? Why do we use control? What the for our non-static dynamics, the control surface is the elevator. So why do we have this elevator? To pitch up and pitch down, yes, but what does it do? What we do is we trim at different CLs. So your CM not equation was CM equation was CM not L into CL. Now, if we want to trim it, what was trim? What was trim? discussed this in the last session. What was right? So trim or equilibrium are synonymous. It is where the sum of all forces and sum of all moments are zero. So basically, in our case, trim is when Cm equals zero. Alright. So to ensure the Cm equal to zero at various different CLs is what the control surface does. That is the aim of the control. So what does it do? The Cm versus CL graph, it translates it. So your Cm versus CL is a graph with a negative slope. So where is the aircraft trim? Here. So this is CL trim 1. So how do you change the CL trim? You translate the graph. So suppose I want to trim at a different CL. I want to trim at the CL trim 2. So this is what your control surface ensures. Now, what two questions here is, does Cm not change? Does Cm alpha change? Does Cm not change? Upon deflecting the control surface, does this value of Cm not, does it change? When I deflect the control surface, my Cm versus CL graph translates. So does the value of Cm not change?
Cm not changes or
Not
different.
change. Yes. So this is your initial Cm naught. This is just new Cm naught. Does Cm alpha change? What change? So Cm alpha, Cm versus CL. So it's similar, right? So Cm versus alpha follows the similar trend. Though not the exact values, Cm versus alpha follows the same trend. Or does Cm alpha change? When I deflect my elevator, when I deflect any control surface, does my Cm alpha change? When I change Cm alpha, what happens? The stability of the aircraft changes, right? So if I deflect my control surface, does the stability of the aircraft change? If it changes, how does it change? Like, does it become more stable or less stable? When I deflect my control surface, does the stability of the aircraft change? Stable, can you try and justify your answer? So when you say less stable, that means your Cm alpha becomes, how does Cm alpha change? Becomes positive. Is that what you are implying? Go back to the CL equation. So just look at the wing and tail contributions. Your control surface is on your tail, so you just have to look at the tail contribution. In this entire tail contribution equation, do you see any terms related to control surface? So VH is the horizontal tail volume ratio. Eta is the ratio to dynamic pressures. CL alpha of the tail is a aerodynamic parameter of the tail. IW is wing setting angle. Epsilon naught is downwards. IT is tail setting angle. VH again, we know all of these terms. So is there any term that relates to control surface? There is no term that comes from control surface, right? These are all pertaining to the tail area, tail dynamic pressure ratio. It's all with respect to the tail, the entire aerodynamic surface. There is nothing that pertains to the control surface. There is no elevator related term in this equation. So what do we understand from it? That the deflection of elevator does not affect the stability of the aircraft in any way. Correct. The CM alpha is the only contributor towards stability. CM alpha wing, CM alpha tail. And in both these equations, we don't find any elevator related parameter. So deflecting the elevator does not affect the stability in any way. Deflecting the elevator does not change the CM alpha. The slope remains the same. So let me just go back. Yeah. So you can see that the graph is nearly translated. So it just moves as it is. It does not rotate. It only translates. So what this does is that CM naught value is changed, but the slope is the same. That means CM alpha or DCM upon DCL is the same. That means the stability is the same. Control surface has no effect on the stability of the aircraft. This question, I think, will be asked quite a few times to test if you've understood it. So control surface deflection does not affect stability of the aircraft in any way. All right, CM naught changes, CM alpha does not change. Okay. Now let's look at a few elevator related terms. So elevator deflecting the elevator downward is considered positive. Okay. Why is it considered positive? Let's just look at it. So I have my friction reference line here. This is my wing. This is CG. Tail. Okay. Now if I deflect the elevator down, what happens that it increases the effective camber of the tail. Right? When I deflect the elevator down, the camber of the airflow, you can imagine it that it changes, it increases the camber. So what happens when you increase the camber? Lift increases. There is a delta L. Delta L that is created due to the deflection of the elevator downward. Downward deflection of the elevator is positive. So with the positive deflection of the elevator, you have an increase in lift. And this increase in lift, how does it affect the moment? It creates a pitch down moment at the CG. Okay. So that means a negative moment. So what happens is positive delta E is how you denote elevator deflection. Positive elevator deflection gives you positive increase in lift and negative change in pitching moment. Correct? Nose down moment. So this delta L gives you nose down moment. Which is why you can see that CL delta E. What is CL delta E? It's CL upon D delta E. So for a positive change in delta E, we get a positive change in lift. So this is a positive quantity. Whereas CM delta E, which is DCM by D delta E. So for a positive deflection of elevator, you get a negative change in pitching moment, which is why this term is negative. Okay. All the other terms, except tau. Tau is control surface effectiveness parameter. Okay. So that's about it. Then we look at the equation for delta E trim. What is delta E trim? the amount of elevator deflection required to trim at a given CL. Suppose you want to trim at this particular CL, you want to let us trim equilibrium. You want to maintain equilibrium at CL trim. How much should you deflect the elevator? So this is the equation that governs that what again. Now let's look at the individual terms. So this is the intercept delta E naught, and this is the slope. So d delta E by BCL, CL trim. So let's just plot this. Now, how will the graph look? So this is delta E, and this is CL trim. So will it be, will the intercept be positive or negative? This CM naught by CM delta E, will it be positive or negative? For this graph, will your intercept be positive or negative? Y-intercept. Delta E naught, basically, is delta E naught positive or negative? Delta E naught is minus CM naught by CM delta E. Is that positive or negative? Positive, correct. So let's just take intersect here. Now the slope. Slope is E delta trim or this CL trim. So it is x bar NP minus x bar CG by CM delta E. Is this positive or negative? The slope. Slope is negative, correct. So you'll have a graph something like this. So this is the graph that gives you how much, suppose I say I want to say a trim at this CL. This is the CL at which I want to trim. If I draw a line parallel to the y-axis, I see how much I should deflect my elevator to trim at the given CL. So that's how you use this equation. Right? Now let's look at a few questions. So the pitching moment coefficient about the leading edge of an airfoil is given by this equation. I think we have done something similar in the last class, where alpha is the angle of attack of airfoil in degrees. What is the trim angle of attack in degrees? It's very simple. You can do it very fast. Can you tell me the answer? You're asking to find the angle of attack at trim. Question is plus alpha. So in this case, we have 0 plus alpha. And we've asked you to find the trim angle of attack. At trim, the CM not CM is 0. 0 is 0, right? Plus 8 alpha trim. So what is the value for alpha trim? Very simple calculation, but what is the answer? Now, is this aircraft statically stable or unstable? And the stability of this aircraft from the data that is given. The aircraft statically stable or unstable? Stable. Why? Because your CM alpha is positive. Your CM alpha is plus 0.0298, which is a positive quantity. So your slope is positive. So the aircraft is not stable. Let's move to the next question. In an aircraft, without changing any other dimension, the distance of the aerodynamic center of tail from CG of the aircraft is increased. Due to this, the change in longitudinal of the stability of the aircraft, longitudinal stability of the aircraft will be. So they have changed this. What is this? This is LT, which is XAC tail minus XCG. Correct? So it's increased. This distance is increased. What will happen to the stability? The stability increase, decrease, remain same, or it's not enough information here to comment.
It increases.
It increases, correct. So let's just look at the formula. So this was the formula of the CM at the CG. So we need to look at the stability. For stability, what do? We look at the CM alpha. This is the contribution of the tail, right? Tail contribution. So this is the CM alpha of the tail. Now in this equation, where does the term, this is RLT, this is NP. It comes in VH, right? So when this is increased, the magnitude of this term is increased. This is increased. So VH is increased. And so the CM, it becomes more negative. CM alpha tail becomes more negative, or the slope is increased. Right? It becomes magnitude of slope is increased. It becomes more negative. And hence the stability is increased. So increase is the right answer. Correct. Then if the distance between the aerodynamic center of the tail and CG of the aircraft, same LT. So this again is LT. Is reduced by 10%. What will be the new area ratio ST upon S in order to maintain same weight? So what we know is VH old is equal to VH new. For this, what should be the new area ratio? Let's try to calculate this and calculate. So, couple of minutes and solve this. It is the right answer, so I'll just solve it. So VH, what was the formula? ST upon S. This is old, so we have old, ST upon S. LT upon C bar, and LT is also old, is equal to ST upon S mu, LT mu by C bar. Now, LT mu is, what is it? It is reduced by 10%. Right, so it is S reduced by 10%, so I'm taking 0.9 of LT old by C bar. And now when you simplify the terms on inside, cut off the common terms, what do you get? You get ST by S mu is 1 by 0.9 ST upon S old. So that is nothing but option 3. You're absolutely right. Next question. With the increase in stability of the airplane, the elevator required for a given CL trim will be more, less, same, can't say. Yeah. So this was the equation for your delta E trim. Now just look at it. Increase in stability of the airplane. How will the delta E trim for the same CL will it be more or less? How much I need to deflect my elevator to ensure trim at the same CL? When I say increase in stability from this equation, what term will change? Shreya says more. Can somebody else also try to answer this? When they say increase in static stability of the aircraft, what term in the equation changes? Or CM equation is CM naught plus CM by the alpha into alpha. And what did I say the stability was depending on CM naught or CM DCM upon the alpha? What was the condition for stability? Static stability. What is the condition for longitudinal static stability? From this equation, can you tell me what is the condition for longitudinal static stability? Condition is DCM by D alpha should be less than 0. So when the stability, when I say stability changes, this changes. So when I say there is an increase in static stability of the airplane, DCM upon D alpha, what happens to the value? Does it increase, decrease? Nature of CM alpha? Increase in stability, what happens to CM alpha? This DCM upon D alpha, what changes? How does it change? Right, so when I change the stability, CM alpha changes. How does it change? When I increase stability, when I say there is an increase in stability, what does it mean with respect to CM alpha? Becomes more negative, right? Greater the slope, greater the stability, greater the magnitude of slope. So if I take two aircrafts, this is A, this is B, this is CM, this is alpha. So is aircraft A stable, more stable, or B? Which is more stable, aircraft A or B? From the graph drawn there, which aircraft is more stable? Aircraft B is more stable, correct, because your slope has a higher magnitude, it's more negative. So when I say there is an increase in static stability, what does it mean? Cm alpha becomes more negative. Magnitude of Cm alpha increases. Correct. So now look at this equation. What changes in this equation? When I say aircraft stability has changed, what changes here? What term relates to stability here? This, right? So when I say there's an increase in static stability, this value is increased. Now, can you try and answer this question? Can you answer the question now? This option, is it more elevated depression, less, same, can't say. Try to solve this, take a couple of minutes. Is it more? Your slope is increased. CL trim doesn't change. I want to trim it at the same CL. What is the value of delta E trim? CL trim is same. So let me draw the graph again. Delta E, CL trim. Okay, so it was like this. It was initially like this. Now with increase in static stability, what happens? The magnitude of slope increases, right? So it becomes like this. So this is 1, this is 2. Just same. Okay. So CL trim, I want to trim it at the same CL. So suppose this was the CL at which I want to trim. CL trim desired 1 and 2. So now can you tell me elevator deflection, do you need more or less for case 1, case 2? This is the CL at which I want to trim the aircraft. CL trim doesn't change. And CL trim, CL can never take a negative value, okay? Just leave aircraft, leave this for now. Let's look at this. Case 1, case 2 for the same aircraft. When I increase the stability, will the delta E required be more or less? Delta E required is on this axis, okay, on the Y axis. Draw a line parallel to the Y axis. So delta E required for the first case is this one. And delta E required for the second case is this one. So for the second case, is it more or less? It's less, right? This is delta E1, this is delta E2. Delta E2 is less than delta E1. Delta E2 is less than delta E1. hence it becomes less. Correct? I hope it's clear to everyone. Okay, let's move to the next question. Positively cambered airfoil producers. We've done this quite a lot of times. What is the right answer? We discussed this even in the beginning of this session. What is the right answer? Correct. So you are asking it over airfoil is looking like this. CP is here, AC is here. I transfer the lift and drag forces to the AC. It comes with a nose down moment. So negative pitch moment at AC. Next question. Similar to the previous case, for a symmetrical airfoil, what will it be? The moment at aerodynamic center, it will be 0, right? The symmetrical airfoil, CP and AC are at the same point. Next, the aspect ratio of an airfoil is, again, we had discussed this in last session and I think in the beginning of this session also. Aspect ratio is V squared by S, yes, it's infinite. Because the span of a airfoil is infinite. The aspect ratio for wing is the opposite of that, finite and non-zero. Correct? Aspect ratio cannot be 0 because you have wings of some finite length. To make a flying wing maneuverable, which of the following requirement must be met? So the aircraft has just a wing. So what is the condition to make it maneuverable? Correct. For a stable configuration, you need CG should be ahead of the AC, right? For a maneuverable configuration, you need AC to be ahead of the CG. Correct? So this is the right answer. To trim a flying wing at negative angle of attack, which of the following arrangement is done? The right answer. To permit at the negative angle of attack for a wing around configuration. So aircraft has only wing. I want to trim my aircraft at a negative angle of attack. So I can So I choose the tapered airfoil, your CM, so that was a formula, so this was the formula, right? Wing contribution. So if I do this, which is the first, you said option one, right? So you should be ahead of aerodynamic center. That means this will become negative. If CG is ahead of aerodynamic center, this becomes negative, right? But that is a condition for stability. So let's not tamper with that. These two correspond to stability and maneuverability. To trim the aircraft, you need this quantity should be negative, right? So you can choose tapered airfoil to be negative. And even if the aircraft is not stable, you can make this tapered airfoil negative and then make it trim at negative angle of attack. So if I have an unstable aircraft, also I can trim it at negative angle of attack. So the airfoil chosen should be tapered. Longitudinal stability of an airplane depends upon this question. I think we did last time. Tail arm, control surface area, type of winglets, none of this. Tail arm, right? So control surface has nothing to do with stability. Winglets again have nothing to do with stability. It's only the tail arm. A negative tail incidence angle setting as compared to zero tail incidence angle setting will result in same static stability, more static stability, less static stability, none of this. Tail incidence angle is IT. So your formula was, this is the formula. So now can you tell me? Tail incidence angle is IT. Yes, static stability. Okay, can you tell me why? So IT only comes in this term, right? IT only comes in the first term. And that is the CM naught contribution of the tail. This is the CM alpha contribution of the tail. So IT does not affect your CM alpha at all. So both 2 and 3 are the wrong answers. So IT does not, tail setting angle, IT only comes in CM naught. CM naught does not affect your stability in any way. I think I've stressed this enough. CM alpha is the only criteria for longitudinal static stability. And IT is coming nowhere in this term. So IT does not change the stability of the aircraft. Same static stability. All right. Is that clear? Like, is this concept clear? Like, why stability is same?
Will that be affecting the CM naught value then?
Sorry.
With the change in IT, will it
Yes.
affect the CM naught value?
Yes, it will affect only the CM naught value, but CM naught doesn't define your stability. It is just where we trim the,
Okay.
yeah, so it only changes CM naught value. It does not affect the stability. Okay. In an aircraft, without changing any other dimensions, the area of the horizontal tail is increased by 3 times. So area of the horizontal tail is ST. Due to this, change in the longitudinal stability of the aircraft will the stability increase, decrease, remain same, cannot say. Again, let's look at the tail contribution equation. So this was ST. When we look at stability, please only look at the CM alpha part, that is only this CM alpha tail. This is CM naught, and that does not contribute towards stability. Only CM alpha contributes towards stability. So when I make the ST 3 times, when I increase ST, will the stability increase, decrease, remain same? Why will it be same? Where can you find ST in this equation? Can you tell me where we can find, is the only thing we're changing in the entire equation or in entire dynamics is ST. The area of the tail is increased 3 times. So only thing changing is ST. Now where can I find ST in this equation? ST is area of the tail. So where can I find ST in this equation? In the tail volume ratio, correct. So which is ST and VC bar. Now ST is being increased. That means VH is being increased. So VH is increased, it becomes, the entire term becomes more negative. So does it increase or decrease, or what happens to the stability? ST increases, VH increases, CM alpha becomes more negative. So what happens to the stability? Can somebody try to answer this? What happens to the stability? ST increases, VH increases. So ST increases, therefore VH increases, therefore CM alpha of the tail becomes more negative. So what happens to stability? Increases or decreases? Or it remains same? What is it? Increases, correct. So the slope is increased, it's the magnitude of slope is increased, right? So it becomes more negative, slope becomes more negative, and so it is more stable. All right. So whenever they have such questions, just see if those questions, those terms feature anywhere in the CM alpha contribution. If it comes in CM naught, stability does not change. If it comes in CM alpha, then you check whether it increases or decreases. Right? Okay. Go to the next question. During a flight, due to passengers' movement, the center of gravity of the aircraft moves away from neutral point. Due to this, the elevator angle required to trim the aircraft will. So this is similar to one of the questions that we had, where CL trim 1 equals CL trim 2. Okay. So in both the cases, we need to trim at the same CL. So now look at the condition. CG moves away from neutral point. So will the delta E required increase or decrease? What was the equation? So the equation was delta E required is delta E naught plus d delta E by dCl into CL trim. And delta E naught was minus CM naught by CM delta E plus x bar NP minus x bar CG by CM delta E into CL trim. Okay. They say that the moment of CG of the aircraft moves away from neutral point. So this quantity increases. So x bar NP minus x bar CG increases. What happens to stability? When x bar NP, the distance between the neutral point and CG, when it increases, stability increases or decreases? Think of this so many times today. Just think about it. So let's just in terms of let's see how stability, let me just write it down. Stability increases, how do we represent it? Okay. So the first case is when CM alpha becomes more negative. Okay. If CM alpha becomes more negative, aircraft stability is increased. Next. Static margin increases. If static margin increases, stability increases. Next. What is static margin? Minus PCM by PCL. So if this quantity increases, that is similar to this, the slope becomes more negative, then stability is increasing. Again, another definition for static margin is X bar NP minus X bar CG. If this increases, stability increases. So now tell me, for our question, does the stability increase or decrease? Increases, stability increases, right? Okay. Now look at the question. So it is very similar to the previous question that we had. So what it says is the center of gravity moves away from neutral point. That is, if the aircraft stability increases, the elevator required to trim the aircraft at the same CL, will it increase or decrease? Previous question that we had seen, right? So it's very similar to that. With the increase in stability, elevator required for given CL trim will be. Shreya, we've just done this question and we have just explained this. Can you tell me why you think it is increased? I think even in the last, when we discussed even this question, you had said increase. So I don't think it's clear. Can you tell me at what point you are facing the difficulty? It just seemed, right? So when stability increases, this quantity increases, which is what is given directly in the question in our current question. When that quantity increases, the slope increases. So your case 1 and case 2, you can see case 2, the slope is increased. So does the elevator required increase or decrease? For the same CL trim. Can you just tell me where you face the issue? It's just for me to know like, which part I'm not being clear. Can you just tell me where you face the issue? Why did you think it was increased? I know it's clear now, but can you tell me where was the difficulty? So I think I have made it clear that CL trim is the same, right? CL trim does not change. We want to trim it at the same CL. That is clear in both the questions for a given CL trim. And our question was. Yeah, so required to trim the aircraft. So CL trim remains the same. Is it clear now? Not just her, all of you, is it clear for everyone? It's the same question, it's just framed in a different way. Okay, please don't get confused. So yeah, so this is the equation that we used, and this is the graph. So I had drawn this graph in the previous case, so this is just that's available. So when the CG moves away, this is XCG equal to X bar NP. Now when the CG moves away from the neutral point, the slope, like the negative slope, becomes more steep, right? It becomes steep. So this is neutral point. This is CG1. This is CG2. This is CG1. This is CG2. So as and when the CG moves away from the neutral point, the slope becomes steeper. When the slope becomes steeper, the delta E required to trim the aircraft with the same CF becomes less. So you can also understand in different ways. So when the CG moves away from the neutral point, the aircraft becomes more stable, less stable. When CG moves away from neutral point, does the aircraft become more or less stable?
More stable.
More stable, correct. So if it's more stable, I only have to deflect the elevator a little bit to trim the aircraft. So it's already more stable. It is already has a tendency to go to the equilibrium point, already has a tendency to trim. So I just have to deflect the elevator a little bit for it to reach trim. So you can also understand it in that way. So when the CG moves away from neutral point, the aircraft becomes more stable, and hence I just have to deflect the elevator a little bit to make it stable, to make it go to trim, not to make it stable, to make it go to trim. Okay, so I'll just draw the graph here. So if this is the CL at which I want to trim. So the elevator required for the CG that goes away from NP is less, right? So this is less than this. Okay, I hope this is clear. All right, so let's go to the next question. Okay, look at the information given in this question. So I think you can do this over the week, and we'll discuss this question in detail next week. But I'll just show you what pointers towards solving this question. So look at the data given in the questions. First, they've given you the pitching moment equation, which is Cm equals Cm naught plus Cm by dl alpha and d alpha into d angle of attack. Okay, so that distribution of that variation is given to you. That equation is given to you. Is this aircraft stable or unstable? Stable, yes, because your Cm alpha is negative. Fine. So you have Cm naught, you have Cm alpha. Then you have what is given to you? The area of the wing, span of the wing, mean aerodynamic chord of the wing, x bar CG, which is x CG upon mean aerodynamic chord, the aspect ratio of the wing, CL alpha of the wing fuselage, the CL alpha slope of the lift curve. It's given in per degrees. Please remember the units very carefully. Make note of it. Then wing setting angle and CL at zero angle of attack. Okay, so this will help you find the CL naught. So this is given to you, and a similar data for the horizontal tail, the momentum, tail momentum, aspect ratio of the tail efficiency factor, CL alpha of the tail in per degrees again. All right. So these are the quantities given to you. What do you have to find? So I'll put up these on the slides anyway, so you can try solving this, and this is how you will solve it. Okay. So they've asked you the contribution of the horizontal tail towards CM naught. CM naught tail using this formula. Okay. Then CM alpha of the tail in per degrees. You can also calculate that given this formula. You have the distribution of the entire aircraft, and they're asking you the contribution of the individual components of the tail in this case. Okay. Then they've asked you to find out d epsilon by d alpha. This is the equation here. Why this is important? You need to remember that all of these equations are only valid in per radians. Okay. Then horizontal tail volume ratio using the formula ST upon S and epsilon naught. And I think this is not the case. IT CM naught tail. So just this is a question that I think you should just take and try to solve, and we'll do it in detail in the next class. But yeah, so I'll put up this on the slide and try finding the values given the data here. So I'll put this up on the slide and you can try solving it. We will go in detail in the next session. So I hope this session was clear. Does anybody have any questions? I think you will have similar questions in assignments that are to come. I think they're already there. You try solving. Does anybody have any questions from this session? Yeah, okay. Somebody had asked me about leading edge vortices in the previous session. So what I was able to understand, one of the instances where how the leading edge vortices are created, that was the question. So one of the cases where leading edge vortices are created is, so let me just draw it here. So what are vortices? When there's a boundary layer separation, usually happens somewhere here, right? So when the angle of attack increases, boundary layer separates, and there is vortex formation here. Now, when there is what is leading edge vortex, these vortices are formed at the leading edge. Why are they formed at the leading edge? There's a boundary layer separation at the leading edge. One of the cases where this happens is where there's a sudden increase or decrease in angle of attack. So when the aircraft is flying at equilibrium or at some condition, there's a sudden increase in angle of attack, either due to pitch up or due to a gust. The boundary layer at the leading edge separates. And due to this, there are vortices formed at the leading edge. So this is one of the ways in which leading edge vortices are encountered. Another case that I'd seen was when there's a high swept back wind. Even in this case, changes in angle of attack lead to quicker boundary layer separation at the leading edge. All right, so these are some of the conditions I saw where leading edge vortices are created. Do let me know if you find out other such situations, but this is what I was able to find out. So are there any other questions? Any doubts, any questions, or do you want me to go over something again? If not, please try to solve this question. We'll do this in the next session. If there are no other questions, I think we'll end today's session. We will meet again next week. Thank you.